Alors, je ne suis pas tout seul dans cette aventure. Je vais demander à Bruno Abdallah Guiderdoni de monter sur scène pour me présenter. Alors Bruno est mon coéquipier dans ce centre, je ne me serais jamais lancé dans cette aventure sans lui. Bruno est un grand astrophysicien, directeur de recherche au CNRS, directeur de l'Observatoire de Lyon, le plus grand de France après Paris. Comme Bruno est quelqu'un de très modeste, je ne vous dirai pas qu'il est dans la liste des 500 musulmans les plus influents au monde, qui est mise à jour par l'université jordanienne, et je ne vous dirai pas qu'il a fait en 2015 le fameux, je ne prononce pas, excusez-moi, Durus Hassania, en arabe bien sûr, devant Sa Majesté. Donc c'est quelqu'un qui connaît très bien le Maroc et qui est intervenu à différents niveaux, voire au plus haut niveau au Maroc. Et c'est pourquoi je suis très très heureux de faire ce centre avec lui. Nous allons donc tous les deux co-animer cette journée. Et avant de lui passer la parole, je précise qu'il y a une troisième personne, vous ne verrez pas, qui est en coulisses, qui s'appelle Luc Tesson et qui lui va faire des dessins. Et Luc, est-ce que tu es là? Est-ce que tu es là, Luc, pour envoyer un premier dessin? On cherche Luc Tesson, et Luc fera des dessins après les interventions. Voilà. Ah, c'est pas Luc, désolé. C'est une intelligence artificielle. Alors bon, ça c'est fait par une intelligence artificielle, mais Luc est quand même vraiment là physiquement. Quand on aura besoin de lui pour des trucs vraiment sérieux, vous savez, les avocats, c'est les intelligences artificielles qui font les trucs toutes seules. Et puis quand on a besoin d'un truc compliqué, on appelle un être humain. Donc pour les dessins compliqués, hop, on fera appel à Luc. Voilà, on aura Luc pour les dessins un peu plus compliqués, je pense. Si on peut avoir le suivant. Donc, je passe la parole à Bruno Guiderdoni qui va vous présenter les intervenants suivants. Voilà quand on a un dessin compliqué, ce qu'on fait.
Merci Jean, bonjour à tous et à toutes. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to everybody. Good morning, I am very pleased to be here. Je suis très content d'être ici au Maroc. Une nouvelle fois, le Maroc est vraiment un pays de cœur, un pays où justement on arrive à vivre à la fois la modernité et la tradition. I will speak in English for the first part of this morning. I am very glad to call the first speaker of this morning, who is Dr. Luke Barnes, who is coming from Australia. He is a lecturer in astrophysics at the University of Western Sydney University. He is an expert in galaxy formation and also in the issue of fine-tuning the fitness of the universe for life. He has written a couple of books with a co-author, Geraint Lewis, A Fortunate Universe, Life in a Finely Tuned Cosmos, and the Cosmic Revolutionaries Handbook, or How to Beat the Big Bang. So he's going to talk about these issues. He's going to address one of the most puzzling problems of modern cosmology, the fine-tuning, the apparent fine-tuning of the universe and the fitness of the universe for life. Please welcome Professor Luke Barnes, and he's going to speak.
There I am, wonderful. Well, good morning. Good morning. If I could speak French, I would, so my apologies. At least you can enjoy this Australian accent. First of all, I should thank all the organisers. Your hospitality to everyone involved has been absolutely spectacular, so many thanks for that. We're here to talk about the question of science and the search for meaning, or the search for purpose. And for previous generations, for almost 2,000 years under Aristotle, this question wouldn't have made a whole lot of sense. To Aristotle, the question of trying to work out how nature works, part of that, an essential part of that, is working out the purpose of objects in nature, as well as working out, for example, for your heart, what your heart is made of, how it was formed, what its structure is. There was also the final cause, the telos of the heart. You don't really understand a heart until you know that it's a pump, until you know what it does. So for 2,000 years under Aristotle, the question of finding purpose in nature, finding purpose in science, were completely connected to each other. That's what it was to study the world, was to find out the purpose of all of these systems. But for the most recent centuries, we've had to ask the sorts of questions that we're asking here today. Is there purpose? Is there sense to be made of the universe? And for the last 100 years at least, especially for the last 100 years, I should say, as Jean was talking about, the question of is there purpose in the universe has been, there have been major, the loudest voices in science, let's say it that way, have been trying to tell us that we are nothing special. We're not in a special part of the universe. We're not on a particularly special planet. There's loads of those. There's lots of stars around. There's nothing special about where we are or the way that our universe is put together. What's changed over the last couple of decades is I want to say that that situation has reversed itself. And it happened in a rather remarkable way. We accidentally started asking the right question. Let me explain. First of all, I can't resist but to put this screen is just, I want one of these in my office. This is a picture of the center of a galaxy from the James Webb Space Telescope. My job as a scientist is to explain part of how the universe works, and in particular, as was mentioned, I'm interested in galaxy formation, of all the ways that you can arrange the objects in the universe, the stuff of the universe, the matter of the universe. Why does it look like that? What physical forces come together to explain the universe we see around us? As a physicist, there's a template for the way that we explain things, which goes as follows. We want three things. I want to know, first of all, the laws that govern the matter in the universe. For example, if tomorrow night you want to know where all the stars in the night sky and the planets are going to be, the first thing you need to know is the law of gravity. What is it that is pushing the planets around? Secondly, you need the initial conditions. What that means is you need to know where the planets and stars are tonight or at some particular time beforehand. The laws of nature tell us how the universe changes, but not how it is. You have to start from somewhere. So you'll need to know where all the planets are, where the sun is, how fast they're all moving, how much they weigh. There's one other thing that you need. Right there in the law of nature, in Newton's law, or if you want to use Einstein's, then have fun with that one as well. Right in our laws of nature, there is a universal constant, G, the gravitational constant. You need to know these universal numbers. And when we dig down to the bottom of physics, to the best explanations we have of the universe around us, we find a large set of about 30 of what are called the fundamental constants of nature. Fundamental numbers, they're not anything more mathematically sophisticated than that, just numbers that tell us fundamental properties of the universe. Let me give an example. If you take the matter we're all made out of and break it down to its smallest pieces, you arrive at three particles called the up quark and the down quark and the electron. In the top right there. Now, I'm going to wander over here. It's very important during a talk to find the funniest part of the stage. That's very important. So I'm going to start over here. So suppose I give you the three fundamental, in Australia I would say Lego pieces. If I say Lego pieces in Morocco, do you understand what I'm talking about? Building blocks. Thank you, sir. The fundamental Lego pieces, the building blocks that we're all made out of. So I'm going to give you up quarks and down quarks and electrons. Now, part of the fundamental properties of those are their charge and their mass and a few other things. Why do these fundamental numbers matter? Well, because these are the building blocks. What can we make out of that? The next, hey, that's not supposed to happen. Let me walk back to the less funny part of the stage and work out what just happened. I assume there's a button on here I accidentally pressed. My apologies, ladies and gentlemen. Oh, Ed Jerome. Hi, Ed Jerome. Wi-Fi off, and we're back. Okay. All right. If this stage was smaller, I'd be going faster. That was the funny part of the stage. Okay, good. I'll come back to that later. Right. What can you make? Well, the first thing you can make is with up quarks and down quarks. Good luck to the translator with quarks. I hope you worked out what that was. I think it's, anyway. You can make protons and neutrons. So there is our next step in towards making something interesting and big. What you can make with protons, neutrons, and electrons is, the next step, atoms. In particular, how many protons and neutrons, this is not working at all, how many protons and neutrons you put in the nucleus of the atom determines what kind of atom it is, and as the electrons go around the outside, you have something which is electrically neutral. Well, what can you make next? Well, what you can do is look at all the different ways that you can put atoms together. The number of protons in the nucleus tells you what sort of atom it is. So we have the entire periodic table of the elements. There are 92 naturally occurring and a couple more laboratory-made versions of elements, of atoms. Well, what can you make with these? Well, if you take the next step and put two different types of nuclei, or perhaps the same type of nuclei, close to each other, the electrons can orbit around the entire thing rather than just around their own home atom, and they bind those nuclei together, and that, in about one sentence, is chemistry. It's not that hard. There's a physicist's version of chemistry. Our universe is phenomenally good at this. You have 92 elements and all the ways you can imagine of putting them together, including DNA. And at this point, I'm way outside of my expertise as a physicist. That thing is more complicated than anything I particularly want to look at. But you can write the instructions for life in these chemical elements. In particular, you can write the instructions for cells. And I'm way outside of my comfort zone as a physicist now, but the code in DNA is precisely a code for the proteins, the basic building blocks of life, of cells. And if you put enough cells together, you can make small people, in principle. So what matters is that all the way back over here, we had those fundamental properties of the fundamental elements of our universe. And what you do as a physicist with these numbers is what we do with them in any other context. We ask the following question: what if? What if the constants of nature had been different? What if I started here, and instead of having up and down quarks and electrons with the masses, for example, that we know they have in our universe, what if they'd been a bit different? This is the kind of question you ask of all the parameters in all your models as a physicist. You want to know, how much does my model depend on the numbers that I have to put into it? So let me take you on a quick tour. There are 3 particles. And one of their fundamental properties, as I keep saying, is their mass, right? Put them on a very small set of scales and see what number comes up. It's a very, very small number in kilograms, but it's there. We know what that number is. So if you've got 3 of those numbers, what you can do is find a 3-dimensional space to represent your choice. I want you to think of this as a menu. What sort of universe would you like to create? So I'm going to take you way back to the beginnings, way back to the fundamental pieces of our universe, hand you some up and down quarks and an electron, and ask what masses would you like them to have? And if you give 3 numbers, that basically puts you in, whoa, giving the game away, that puts you in this block. So the way I've done it, there's a top limit there. There's a limit to what our equations can handle, something called the Planck mass. I won't go into the details there. There's a reason for the limit at the bottom as well. And what's represented here is 60 orders of magnitude, 10 to the power of 60 sets of choices. Now we, as you can see, are there, conveniently labeled if you want to find us. But what happens if we change these numbers? Well, let me give you a quick tour of this space. What I'm going to do is I'm going to help you out by carving off parts of the block here, this space, that if you want an interesting universe, you probably want to avoid. For example, press the right button. I've carved off those two regions around the back. Why don't you want to be over there? Well, allow me to explain. Remember the first step that we took? I've given you up and down quarks. Step one was I made protons and neutrons on our way to making complexity in the universe. If you end up in that region of the block, you don't make protons and neutrons, you make another type of particle out of the quarks called either, memorably, the delta plus plus particle or the delta minus particle. There's no exam at the end. Don't worry if you don't remember the details. Here's the important thing. Let's start our journey again in these universes. I've given you the up and the down quark and the electron. You can put three of the quarks together to make the delta plus plus over here or the delta minus particle. And then our story is over. We're stuck here. A delta particle of either kind will not stick to itself. You can't make anything out of it. We're done. The story of the complexity of the universe is over here. We don't get anywhere near the complexity we see in our universe. In other parts of this space, right, so here is a picture of the atom. There's no quantum mechanics yet, so just enjoy this lovely classical picture of the atom before things get a bit bananas later on. Good luck. Good luck translating bananas. Here's a classical picture of the atom. If you don't get even if you have protons and neutrons, if you don't get these numbers right, when you arrive at the next step of trying to put together atoms and molecules, you'll find actually that these don't stick to each other. Actually, if you get it even worse, you can make the electron spiral into the nucleus and make a universe full of neutrons. Here's why that matters. Here's the periodic table again, which I hope you're at least somewhat familiar with from high school. This, just for some fun, this is the astronomer's periodic table. I'm an astronomer. It's colored according to where that element is made in our universe. So whether it's made in the Big Bang, in large stars, in supernovae, in small stars. If, when I sent you back over here to order your universe, if you get the numbers wrong, then rather than a periodic table that looks like this, you end up with a periodic table that looks like this. Right? In this universe, the chemistry textbook goes as follows. There is one element. We might as well call it hydrogen. There is one chemical element. It's the hydrogen molecule. There is one chemical reaction. You can make a hydrogen stick to a hydrogen to make a hydrogen molecule, and that is the end of the chemistry textbook. Unfortunately, there's no one around to read it or anything to write it on, but it would be a wonderfully simple chemistry textbook. Here's the point. Once we've taken all these factors into account, the part of the set of possibilities that allow us to go from the ingredients of the universe to anything like the structure we see around us is an extraordinarily thin slice of the set of possibilities. Excellent. What I actually do for a living is simulations of how galaxies form. If you put the best physics we have into the biggest computer they'll let you use, and you let it run for a month and a half on a supercomputer, and you've done your physics right, what you see at the end of it is something that we hope represents something like how galaxies form in our universe. The universe starts off almost perfectly smooth, but as time goes on, as the universe expands, the expansion is factored out here, so you don't see that. Gravity pulls matter together so that the densest part of the universe get even more dense, the rich get richer, and so the universe forms structure. By the way, that number down in the bottom left to you is counting away in billions of years, so this is the fastest fast forward you've ever seen in your life. The structure we see at the end, when we get to today in the universe, is what's called the cosmic web, hopefully for obvious reasons. It looks a little bit like, well, spiders' webs are neater than this, but that's the idea. We see parts of the universe that have been emptied out, the cosmic voids. We see dense parts of the universe known as the knots, where galaxies and clusters of galaxies and clusters of galaxies form. And in between there are these web-like filament structures which haven't quite decided which way they want to fall just yet. With some colleagues of mine in various places in the world, including Durham and Western Australia and some other places, we use that same code, right, known as the Eagle code for various reasons. It's an acronym. We use that same code and asked, okay, what if, rather than going all the way over there and changing the masses of the fundamental particles of the universe, what if we changed the way our universe started? What if we changed the way that it expands? And there's a very important number underneath it all, behind the scenes of the way that our universe expands, known as the cosmological constant. Here's the short story. We've known since the 1920s that our universe is expanding. If you look at a galaxy out there in the universe, it is moving away from us. And it's moving away in such a way that a galaxy twice as far away will, on average, be moving twice as fast away from us. That's what gives us the uniform expansion. What we've known since 1998 is that not only is that galaxy moving away from us, it's moving faster today than it was yesterday. That number, that tendency, which no one was expecting, of the expansion of the universe to accelerate is captured in a number called the cosmological constant. We don't know why it is, what it is, but what we can do, and what we have done in these papers, is to ask, what if it had been different? There is a range of these numbers consistent with our model. Everything is mathematically fine over a range of values. What if we went exploring through these values? What if? So when I press play on this slide, it's going to show what we found. On your left, the left third is going to show roughly our universe, where structure will form. In the middle panel, we've taken the cosmological constant in our universe and said, what if it was 10 times larger? And in the panel on the right, we said, what if it was 100 times larger? Now, that might sound like a big amount, but relative to the overall possibilities, that's actually a very small range of changes. So, using the same code, using a supercomputer, you cross your fingers and hope nothing happens to the supercomputer while you do your work. These are the simulations that we were able to run. They start off the same because this acceleration of the universe doesn't sort of make a difference until later on. But what you can see is on the left, structure is forming as we see in our universe. Whereas in the middle and on the right, this tendency of the acceleration of the universe, this faster expansion rate, means that that process of galaxies pulling things in with their own gravity to make them larger has stalled, and structure doesn't form. So instead of our universe, where the story would go something like, we start off with a very smooth universe, and then gravity starts pulling galaxies together, and then within galaxies stars form, and then around stars forming, planets form. On the right here, if you get this number wrong, you end up with a universe that forms very, very little structure, and if we made that number slightly larger, it wouldn't form any structure at all. This fact is known as the fine-tuning of the universe for life. This is the book that I wrote about this with Geraint Lewis. A summary is as follows. Of all the possible values of the fundamental constants of nature, the subset that permit the existence of life seems to be very small. Geraint Lewis is a colleague of mine from the University of Sydney. He is also an atheist. We wrote the book together, and the first 7 chapters we agreed about everything, except for one footnote that you can go and find. enjoy that later on. By the way, it's available in Arabic, but not in French. My apologies. I don't make those decisions. And Chinese. We agree on this science. The science that I've just presented to you is something that he could have just presented to you. This is not something outrageous or weird, or it's definitely something weird, but it's not something that is on the fringes. It's right there in the middle of the physics literature. And it's a very active field of research. I have a new student who's starting to work with me at Western Sydney. We are going to do more of these simulations, working with our colleagues to try and work out some more details about what would happen if these numbers had been different. As I said, so if anyone wants to come to Western Sydney University and help me do these as well, that would be great. I noticed the university here just signed a memorandum of understanding with a supercomputer. I was there for that yesterday. That was very interesting. If anyone wants to use that supercomputer to do something interesting, come and join me. Why would you come and use facilities in Australia? Well, we have something very important at our facilities. We have kangaroos. If you can't see those, they're very cute. Good. What does all this mean? I mentioned that Geraint and I wrote 7 chapters of the book together. The book has 8 chapters. We disagree about what this means. So what does it mean? Well, whenever I'm asked to talk on the topic of, is there purpose, is there meaning, is there design in the universe, it's very, very tempting to say something along the following lines about fine-tuning. This is a quote that was not said to me, it was said to someone else. I'm not religious, but something weird is going on here. About fine-tuning, there's something weird going on here. The story of 100 years of physics, at least, that where nothing special, nothing interesting, nothing important has been turned on its head. Now, there's 2 things you could do at this point. One of them, which I just want to point towards but not go into in detail, is to take the philosopher's approach of trying to mold this into an argument for the existence of God, the fine-tuning argument as it's known. Now, I'm more familiar with English language philosophy, of course, and I'm not a philosopher, I'm an astrophysicist, as I mentioned. These are the names that have done an awful lot of work in this field. It's in the analytic tradition, if you know philosophy at all. What I'm interested in is, especially in an audience like this, are there names that I'm missing? Because there's a large part of the world that doesn't speak English. So these are the names that you can look to. I've tried a little bit of this myself. Here's a paper of mine, A Reasonable Little Question, a formulation of the fine-tuning argument. You can do all of your analytic philosophy if you really want to. You can formulate your premises. You can talk about likelihoods, interpretations of probabilities, the probability that life permits here and there. You can break it down into the premises, and that's something I'm obviously very interested in. But I actually want to take a different approach today. I want to talk about the design intuition. Richard Dawkins, perhaps the most famous atheist, at least in the English-speaking world, wrote a book called The Blind Watchmaker. And he said the following: biology is the study of complicated things that give the appearance of having been designed for a purpose. Physics is the study of simple things that do not tempt us to invoke design. Here's what I think he is saying. If you look at biology, if you look at living things, the temptation to see design is overwhelming. Like I said, when I'm asked to speak about design in the universe, it is very, very tempting to put that video on screen and then say nothing for half an hour. What more could I possibly add? So if you can't see design there, I can't really help you. When I started doing this, I should say, when I started using the example of a hummingbird, I'm not sure what of my devices was listening in on me, but Facebook started trying to sell me this. I haven't bought one yet, but I'm very, very tempted. If you can see design here, that doesn't actually fly. The other one does. It flies. It really flies. how do we see design? What is it about that obviously says design? Well, I actually want to quote Dawkins on this. Here's what Richard Dawkins says. I'll read this whole quote for you. I think it's quite important. When Dawkins says that biology gives the appearance of design, what does he mean? He means the following. It is true that there are quite a number of ways of making a living, flying, swimming, swinging through the trees, and so on. But, however many ways there are of being alive, it is certain that there are vastly more ways of being dead, or rather not alive. You may throw cells together at random, over and over again for 1 billion years, and not once will you get a conglomeration that flies, or swims, or burrows, or runs, or does anything even badly that could remotely be construed as working to keep itself alive. Where do we see design? Well, here's one way that we see it. If you took all the cells of the hummingbird and just threw them together at random, you would not make something that flies. There is something that gives the appearance of design in the arrangement that would not, of an actual hummingbird, that would not be there in a randomly thrown together hummingbird. Now, what Dawkins wants to say at that point is that evolution does not throw things together at random. That's the whole point of Darwinian evolution. That's not my point. I'm not here to talk about biology. What I want to point out is that he's given a method. He has asked the question, what happens if you throw cells together at random? Well, we can do the same sort of thing. We can ask, what if we throw a universe together at random? What if we were able, obviously not in practice, but at least in our best theories of nature, what if we could simulate the process of throwing a universe together at random to see whether there's anything interesting about this universe, to see whether it flies? And what fine-tuning points us towards is the fact that if you throw a universe together at random, it doesn't fly. Nothing interesting happens. You get stuck all the way over there. You have pieces that don't stick together. You have a universe that just expands too fast and never makes structure. What you don't get is a universe like ours, which has the ability to turn its basic constituents into the kind of thing that can think about its basic constituents. So at that point, I'm going to finish. There's the book again. This search for meaning, I want to say that in fine-tuning, the question has reversed. Once again, we find ourselves in a situation where actually the purpose, the design of the universe is now the thing that seems most obvious at a bottom level. Once you've learned, and we did it accidentally, but once you've learned to ask the right question. Thank you very much.